All right, our purpose here is to talk through some of these volume and differential equation homework problems, and so you can check your progress and see if you're on the right track. We're going to start with number 13 on page 428. The first question is to rotate it around the x-axis. I'm just going to set this one up, not solve it. But if you're rotating it around the x-axis, this is going to be a washer method, and you have a big radius and a little radius. The big radius is just the upside down parabola. All right, and because we're rotating it around the axis, we don't have to add or subtract anything. We just need to square that distance, and that distance is given by the equation. And then the little radius is the regular parabola, and so that's just x squared. Remember, for washers, it's basically pi on the outside, big R squared minus little r squared on the inside, and this is one that if we needed to square out and to evaluate, we could. The second one is to revolve it around y equals 6. So we're going to revolve the next one around this horizontal line up here at y equals 6. So that kind of changes our radii a little bit. The first radius is going to be from that axis of revolution down to the farthest away edge of this two-dimensional shape. And so that's to the upside down, or that's to the right side up parabola x squared. So the distance of that green arrow right there is 6 minus x squared. Okay, the distance from the x-axis up to the graph is x squared. The full distance is 6, so subtract the 2 and you get the big radius. The little radius is just 6 minus the other function, quantity squared. So that's going to be 6 minus 4x minus x squared. And all of that's getting squared. Remember to put your function in parentheses because this negative is going to apply to both parts inside there. Now I'm going to halfway evaluate this one. I'm going to skip through some of the algebra. If you had to do this one by hand, it would be a long one, but it wouldn't be impossible. We would square this out, and that does not mean distributing the square. It means foiling. Write it twice and multiply it by itself. And then squaring this one out, that would be a kind of a big mess. You'd have to square this 3-term, this trinomial, which would create a lot of terms. What happens in the long run is you've got so this is going to create an x to the fourth when you square that, and this one's going to have a minus x to the fourth. So the x to the fourths are going to cancel out. You're going to end up with a factor of 8 on the inside. I'm going to skip through some of the algebra. You should do that algebra once or twice for practice, but I'm going to, for the sake of time, show you where you would end up. Once you squared everything out in combined like terms, you would end up at x cubed minus 5x squared plus 6x, and we've taken a factor of 8 out because we would have had 8x cubed and 40x squared and 48x, but we just went ahead and took the 8 out. Now once it's to a point like this, and I skipped several minutes worth of squaring and combining like terms, now we are ready to finally take the antiderivative. When you take the antiderivative of x to the third, you get x to the fourth over 4. 5x squared becomes minus 5/3 x cubed, and 6x is 3x squared. And we're going to plug in a 2 and a 0 into that. The 0 is going to basically wipe out. When you plug in the 2 and multiply the result by 8 pi on the outside, you're going to get 64 pi over 3. All right, so there's some checkpoints. When you do all of your algebra and combine like terms, you should check that you end up right here. When you anti-differentiate, you should check that you end up right here. And when you plug in the 2 and 0, make sure you end up right here. But like I said, for the sake of time, we're not going to do all that on this particular video. Next question is to take this two-dimensional area that is defined by these two graphs, and we're going to rotate it around. No, not rotate it. We're going to build a solid of known cross sections, and one of them is a square, and that would be side length squared. And the side length is just the distance between the two functions, which is shown here. So if it's a square, we're just going to square that length. Imagine a square coming up out of the screen towards you, and however long that square is, which is determined by however far apart these two graphs are, that's going to be the height that's coming towards you. So sometimes the words length and width and height get kind of jumbled in a situation like this because we're talking about 3 dimensions, and all you need to know is that there's a side length, and you need to square it, and that side length is however far apart the 2 graphs are. The second question was, what if it's a rectangle with height 1? And basically that just means we don't square that function. Instead, we multiply that length that we used before by 1, because this rectangle only comes out of the screen 1 unit. And we're going to do some of this one by hand. If you combine like terms before you integrate, I get a negative x squared from here. This negative is going to distribute. I get a plus x and a plus 2. Right? Probably 80% of these problems is algebra. So you've got to be careful with your distributing negatives and combining like terms and squaring correctly, that sort of thing. Only 20% of this is setting it up and doing the calculus. So you have to be good at your algebra and be careful. When I integrate this, I get negative x cubed over 3 plus x squared over 2 plus 2x. And I'm going to substitute in a 2 and a negative 1. Remember that when you substitute in 2, you're going to get a number, and then subtract what you get when you substitute in negative 1. And those 2 values, when you subtract them, you're going to get 9/2, or 4.5. All right, so check that you can go from here to 9/2 by subbing in 2, subbing in negative 1, and subtracting the 2 results. Okay, this next one, it was a little bit more challenging, a little bit of a twist on the shell method. It says we're going to create a machine part by rotating the graph of this semicircle around the y-axis to create a hemisphere, or a half a sphere, and then we're going to drill a hole through the middle to remove 1/3 of its volume. So here's the approach I took. I first figured out that if the hemisphere were intact, it would have a volume of 18 pi. The volume of a sphere is 4/3 pi r cubed. Since I have half, I'm going to cut that in half, and I'm just going to substitute in the radius of 3, because this hemisphere's radius is 3, and get 18 pi. Now, working with that, if I'm going to drill a hole in such a way, and the thing I don't know is what's the radius of this empty space in the middle. Actually, the question is, what's the diameter? So my question is, how big of a hole should I drill through it so that I remove 1/3 of the volume? Well, I know that if I'm removing 1/3 of the volume, that's 6 pi. So what I'm going to do is basically set up a shell method that results in 6 pi, because that's the empty space. So think of basically the volume of this empty space that's missing throughout the middle. That shell method, it's 2 pi times radius times height. The radius is just x, because I'm spinning it around the x-axis. Remember, radius doesn't really concern what function we're using. It's always x, or x plus a number, x minus a number, that sort of thing. The height, since this thing's resting on the x-axis, is just the function. That's the function given in the question. And so what I need to do now is have an unknown of k, because I don't know where I'm going to stop integrating, but I do know that my answer is 6 pi. And we see this a lot on AP-style questions, where they're just mixing it up on us. We find volume after volume after volume given the limits, but this time we're going to find the limit given the volume. So k is our unknown. K is actually the radius if we're going from 0 out to k, and I'll double that at the end. So this one's, again, has a lot of algebra in it, but let's set this one up, and I'll at least get it set up and get you on the right track to solving it. So first of all, let's realize that this integral from 0 to k must equal 3. And I'm going to rewrite it in the process 9 minus x squared to the half instead of a square root. But it's going to have to equal 3, because if 2 pi times this integral equals 6 pi, then that integral must have been a 3. In other words, I'm going to divide both sides of the equation by 2 pi. Now let's integrate this thing. U equals 9 minus x squared. This is a classic U substitution. Du equals negative 2x. We need to squeeze a negative 2 inside the integral and a negative 1/2 outside the integral. This is the type of thing that you get good at during the chapter that you're working on it, but it's easy to forget how to do. So this is good practice for a long enduring skill that you need to be able to have. So what is the integral of something to the 1/2? Right? So we're integrating u to the 1/2. We've already fixed du. The integral of something to the 1/2 is that thing to the 3/2 over 3/2. So the first thing I'm going to do, instead of dividing by 3/2, I'm going to multiply by 2/3. And that 1/2 has become a 3/2. And some of you are more comfortable actually substituting out the x stuff and going into a u expression and then integrating and get u to the 3/2 over 3/2. Kind of taken out that step and skipped right back to where I subbed in. So if you are more comfortable, by all means, substitute out the x's and put in u's and then substitute them back. So now I just need to solve this equation. I left off my limits. K to 0, k is my unknown, but when I anti-differentiate, I need to plug in k and plug in 0. These 2's will cancel, so I have negative 1/3 in the front. And when I sub in k, remember that's an x value, so I have 9 minus k squared to the 3/2. That's what I get when I sub in k. When I sub in 0, I get negative 1/3. 9 minus 0, or just 9, to the 3/2 equals 3. And to not do this entire thing, but to get you on the right track, let's see. This term over here, 9 to the 3/2, that's 9, the square root of 9, which is 3. 3 cubed is 27, times negative 1/3 is negative 9, but it was minus negative 9, so this all becomes plus 9. All right, you can confirm that. I know I didn't show many of that in many of those steps. So if I subtract 9 from both sides, I'm going to get this expression equals negative 6. And how are you going to solve for k? So here are the things that need to happen. I'm going to multiply by negative 3 to get rid of this. And then I'm going to raise it to the 2/3 power to get rid of the 3/2 power. Then I'm going to move k squared to the right, and I'm going to move that number to the left, and then square root. And I know I'm leaving out showing all that, but to solve this equation, those are the steps. Multiply by negative 3, 2/3 power, subtract k squared from both sides to get it on the right. So it's going to be 9 minus your number, and then square root to get your answer. And the final answer for k will be 1.46, leaving a little bit of that to you. And so if that's the radius, then the diameter is 2.92. But again, this would take 20 minutes to do every single bit of it, so I've got it set up for you. I'm going to let you handle the algebra. All right, finally, a differential equation. Try to make this one quick. In order to separate, I need to first think of y prime as dy dx. And what I'm going to do first is take this entire thing and subtract it from both sides. Now I can separate. So I'm going to divide both sides by y. And I'm going to move the dx up and to the right, but instead of having a negative outside the parentheses, I'm just going to distribute it. It's easier to deal with separate terms when we're integrating. So now I've separated, I want to integrate. The integral of dy over y is natural log of y. That, we're going to see that a lot. The integral of negative x is negative x squared over 2. The integral of 1, or negative 1, is negative x plus c. Now I've told you in these situations where you have natural log of y on the left, I think it's easier to solve for c later. I think my next step is to e both sides. And e to the log y is y. And on this other side, e to this sum of three things is c e to the negative x squared over 2 minus x. That's all my exponent. And remember, when you do e to a sum of things including a plus c, it turns into multiplication, which we've talked about in class, but is easy to forget. This addition turns into this multiplication because of the rules of exponents. So now I need to sub in and solve for c. I know that y is 1 when x is negative 2. So when x is negative 2, I get negative 4 over 2 minus negative 2. And these usually work out fairly nicely. That's e to the negative 2 plus 2, which is e to the 0. And since e to the 0 is 1, c becomes 1. So my answer is 1e to the negative x squared over 2 minus x. And I believe your book combines the fractions in that exponent and gets e to the negative x squared minus 2x over 2, but either one of these is okay. All right, so remembering that c times right there is by far the most common mistake because it's using exponential rules backwards that we usually use forwards. So overall, separate, integrate, solve for y, solve for c. Sometimes we'll solve for c first, but in this case it was a lot easier to isolate y first and then get c.